Okay. Hello, everybody. I hope we are all doing well. Um, I trust that we are all religiously following all the regulations laid for us to prevent coronavirus at home. And I'm really glad and I really like to welcome us to this session. This is the third episode of our Tensorflow Dev Summit Nairobi 2020. We've had a couple of sessions before. The third one, if in case you missed any of our previous sessions, you can just check our GDG Nairobi channel, and you can get to speed with what has been happening concerning TensorFlow. But as for today, we are going to have a very, very, how will I put it, important guest here who is going to be speaking to us about deep learning core concepts with TensorFlow. And a little bit information about our speaker. His name is Derrick MWITI, who is a data scientist who has a great passion for sharing knowledge. He's an avid contributor to the data science community via blogs such as Heartbeat, Towards Data Science, Datacamp, Neptune AI, KDNuggets, just to mention but a few. He's also an author and an online instructor. He trains and works with various institutions to implement data science solutions, as well as to upskill their staff. So some of the organizations that he has worked with include Innovation Hub, ICPAK, Kenya Tourism Board, NSSF Uganda, Kenya Agricultural and Livestock Research Organization, just to mention but a few. This shows that Derrick is, the expert in this particular field, and it's really an honor to have him on board today to speak to us as the GDG Nairobi community and talk to us about deep learning concepts in TensorFlow. Yeah, he's an alumni of Multimedia University of Kenya, where he studied maths and computer science. He's also an alumni of Meltwater. When he is not playing, he enjoys reading and traveling. You can also catch him on Twitter via the handle @_MWITI Derrick. So in case you want to follow up or ask more questions. And well, concerning questions, we'll be running a live Q&A session. So if you have any question that you want to direct at Derrick, you can post your questions on the Slido link that will be shared to you shortly, or you can just go to Slido.do and input the ID #GDG Nairobi, and you can access the live Q&A platform where you can put your questions and we'll be able to address them later, probably at the end of the session. So at this juncture, I would like to welcome Derrick to take us.
Thank you so much, Tabi. I think we'll just get started. So in this session, I'd like to just take you through what we'll cover. So we'll be talking about neural nets, activation functions, cost functions, optimizers, and then back propagation. And so we'll start off by talking about what artificial neural networks are. And as we all know that, they're just computational models that have been built to mimic the working of the human brain. And as we can see, the dendrites represent the inputs, that is the data you'd pass into the neural network. And these terminals, the axion terminals, they represent the output. And so this, on the right side, what we can see now is an example of an artificial neural network with one hidden layer and the input and the output layer. And so usually what we do is that we pass in our data on the input layer, and then the computation will happen on the hidden layer. And then we get our output on the output layer. And so in this case, it's just the model has just one hidden layer. But in the event that you have two or more hidden layers, then that you would call that a deep neural network. And so what happens when you load in your data set? For example, as you can see in this diagram, you have your values from x1 all the way to xi. And so what happens is that when the passed through the neural network, the first thing that happens is that weights and biases are initialized. And so, for example, as you can see here, y is equals to w1 plus x1 all the way. So you can see that we have weights and we have a bias, that is b1. And so the bias is essential to ensure that we do not encounter just zeros in our computation. So when your neural network weights is small numbers. So as you can see in this equation, not the equation, but in this initialization model is equals to tf.keras, we're initializing the weights using kernel initializer. In this case, we're just initializing them to a uniform distribution. And then for the biases, we are just initializing them using zeros. So once the data passes through the neural network, the first step is that the weights will be initialized as well as the biases. And so this is just a quick example of how this computation works. So you add some input x that is multiplied by the weight, and then you add a bias, and then you get your output y. So of course, before you get your output, there's something that happens in between there, which we'll talk about in a few. And so in Keras or in TensorFlow, you can initialize your weights and biases using a random normal distribution, or you can initialize them using a uniform distribution, or you can just initialize them using zeros and ones. And so this is what I was talking about. You input your data set, your X values, that is your features, and then they are passed through the activation function, and then the activation function determines the output. And so now let's talk about the activation function. What activation functions are? The functions to determine the output. So for example, if you input your values, there's a specific output that you'd like to get. Let's take an example. You'd like to predict whether a customer will churn or not. So what you want as your output is the probability that this customer will churn or not. And so what is the range of a probability? It's usually between 0 and 1. And so now using an activation function, you can constrain the output. So there are certain activation functions you use that will contribute to a number between 0 and 1. In the case of predicting for churn, for example, you'd like to get the output to be a number between 0 and 1. That is the probability. And of course, the class that would get the higher probability is the class that would be chosen. And so, for example, in using TensorFlow, once you define your model, as you can see, you can define your activation function. And so what we can see, this is the first layer, and then this is the second layer. And we can see that in this layer we have an activation function, the ReLU activation function, and then in this layer we have the Sigmoid function. And so what we can see is that in the hidden layers, we mostly use the ReLU activation function, while in the output layer, we can either use the Sigmoid or the Softmax, as we'll see in a minute. And so the ReLU activation function, usually, as you can see in this graph, will cap your outputs from 0 and above. So use this in the hidden layers. So this will ensure that the output you get will range from 0 and above. So you will not get any negative values. And so mostly we use the ReLU activation function in the hidden layers. And then we have Sigmoid. So the Sigmoid function will will ensure that the outputs are between 0 and 1. And so mostly we use it for binary classification. And then there is a variant of the sigmoid known as Softmax, which we mostly use for multi-class problems where the labels are exclusive. And so just to recap what we've seen so far is that you input your data set, X1. So these are the features from X1 all the way to XP. And then weights are assigned. Weights, and each of the neurons will have a bias. And so once the computation happens at this place, they'll need to pass through an activation function. And for example, we can use the ReLU activation function. So the ReLU activation function will ensure that all the values will be 0 and above. So now, after that, the results of this will be passed to another activation function that will now dictate the output, Y. So now, what's the difference between a sigmoid and a softmax? So when would you use sigmoid versus use of the softmax activation function? So you use the sigmoid when you have non-exclusive classes. So let's take an example of a picture of Nairobi, for example. A picture of Nairobi could have a car, a building, and a tree in it. And so just because, for example, there is a car in the picture doesn't mean that we cannot have a tree in the same picture. So these classes are non-exclusive. So just because one class is there doesn't mean that another one cannot be there. So in this case, you can have a car in the same picture, you can have a building, you can have a tree. So there's more than one right answer. So in that case, you would want to use a sigmoid activation function. But then in the case that the classes are mutually exclusive, you'd want to use the softmax. So for example, if you're classifying a picture as either grayscale or colored, so in that case, you cannot have a picture that is both grayscale and colored. So the activation function you'd want to use in that case would be softmax. That is, there is only one right answer. And so there are other differences between the sigmoid and the softmax. So usually we use sigmoid for binary classification, and then we use softmax for multi-classification. And then the output you get from a sigmoid activation function, they do not have to add up to 1. But then when you're using the softmax, the probabilities you get will sum up to 1. So if you sum up all the probabilities you get from a softmax activation function, the answer will always be 1. However, the values you get from a sigmoid activation function will not always add up to 1. So now the next thing you'd want to know about is the loss function. So now, going back to this example, so you have your values x1 all the way to xi that you pass through the network, and then you get your result. So the question is, how does your network learn? How do you getting the right result? So you can start comparing the result that and the price of a commodity, and your model, for example, gives you the value as 10, whereas the true value is, for example, 20. So what you want to do is you want to compute the differences between the predicted values and the actual values. And the way you do that is by using a loss function. So this is what will help you in ensuring that your network is learning. And the way that is done is that once you compute these differences, you adjust the weights. So when the weights are adjusted, the network will be able to learn. And so your goal is to ensure that the error you are getting, that is, you reduce the cost function, or what you're calling the loss function. So that's usually your goal, to ensure that the cost function is at its minimum. And so in TensorFlow, there are several loss functions that you can use. So for example, in a binary classification problem, you can use the binary cross entropy. In a multi-class problem where your labels are one hot encoded, we use the categorical cross entropy. However, if you're working in a multi-class problem where the labels are encoded as integers, we'll use the sparse categorical cross entropy. And then the mostly used loss function in regression is the mean squared error. And as we can see from this graph, your goal is to ensure that the loss function on the training set is reducing, as well as the loss function on the validation set. So in the event that your loss function is increasing, then it means is going up. It means that the model is not learning. And so the way you're able to monitor the loss functions is by using you can use, when you feed your model, you usually have access to history which you can use to plot the loss function, or you can use a TensorFlow callback, and you can check this using TensorBoard. The other way you can do this is just by checking the loss as your model is training. And as we check, and as we can see from this picture, we notice that the loss is increasing. It's decreasing, and that's how it's supposed to be. Otherwise, if it's decreasing, then it means that the model is not learning. But then there are some times when you are training your model and then you notice that you have some NANs in the loss. As we can see in this picture, the loss is not a number, there is just NAN. And so the way you deal with that, number one, is that you need to clean for any null values in the data set. That could be one reason that there are NANs. The other reason why there could be NANs is if you've done any computations that would result to NAN or infinity. For example, if you division by 0 somewhere in your operations, that would result in a NAN, which would cause you to have NANs in your loss function. The other thing that would lead to getting NANs in the loss function could be your data is not scaled. We know very well that in deep learning, you have to scale your data set. This is to ensure that your model, you don't have any challenges when your model is learning. And the reason you have to scale your data set is because even the weights, when they initialize to also small numbers. So it's always a good practice to scale the data set. And one of the ways is either by normalization or standardization, such that the minimum is 0 and the maximum is 1. Other operations that would result to getting NAN is, for example, a square root number. That would result to an NAN in your loss. So when this loss function is computed, how is it propagated back to the network? And so this happens through a back propagation, or by use of an optimizer function. And so this is what we'll look at next. So during the training process, our goal is to get the minimum loss function. And so the way we do that is by using a gradient descent. And so that what happens is that you differentiate to find a slope at a specific point, and you find out whether that slope is positive or negative. So what you want to do, as we can see in this picture, is descending to the minimum of the cost function. And so what happens is that back propagation will compute the gradients of the loss function with respect to the weights. And so as this happens, now the model is learning. And as we can see, as we descend here, we are taking some steps. And so these steps is what we call the learning rate. So we specify this as the learning rate. And so this is done using the optimizer functions. And there are of them, but the mostly used optimizer function is Adam. And so in most of the cases, you'll find that that's the one we use. And so if we go back to this example, so what happens is that we will input our data, the features, and then some random weights will be initialized with the bias, and then the computation will happen in the hidden layer, and then you get some output, and then the difference between this, the output and the true values is computed, and once that is done, you can then use gradient descent to minimize the loss function. And then you propagate this back to the network and you adjust the weights. So the weights are adjusted to reduce this loss function. And so there are various types of loss variants of the gradient descent. One of them is batch gradient descent. And this, what happens is this one uses the entire data set to compute the gradient of the cost function. So this one will be slow because you have to compute the gradient descent of the entire data set before you can perform a single update of the weights. And then you have another one known as the stochastic gradient descent. And so this one will compute the gradient descent using a single training example in every iteration. And so this one is a bit faster, but also if your data is large, it might also take a while. But then there's also the mini batch, which will take a batch of the training data and use it to compute the gradient descent of the cost function. And so the mini batch might be a good choice if the data is very large. And so we've got to the end. And so what we've covered so far is that we've learned, we saw the overview of the neural networks, that they're just computational models that have been built to mimic the working of the human brain. We've seen that we use the activation functions to constrain the output that we get from the network. We've also seen that mostly in the hidden layer, we use the ReLU activation function, which ensures that the output is between zero and above. And then we've seen that in the output layer, we can use an activation function which will also constrain the output at that layer. And we've seen that some of the activation functions we can use at that point is the Sigmoid or the Softmax. And then you've seen that we use the cost function or the loss function to compute for the differences in the predicted output and the real values. And then we use back propagation and optimizers to propagate this back to our network, adjust the weights, and then improve our network. That's it. Tabi?
Okay, so I was just working on the platform where we get to ask questions. But yeah, I can see that you are already done. That's it?
That's it.
Okay, that's nice. Thank you so much for that. Just give me a minute to check if we are able to get any questions from the audience. Even though this was late, the platform ran late. Okay. Okay. Give me a minute. Well, so so there's this question where the main topic today was deep learning, and you know, someone might wonder what exactly is the difference between usage of TensorFlow in deep learning and machine learning. Is there like really a big difference, or maybe if you could expound more on that?
And so deep learning and machine learning are both subsets of artificial intelligence, but deep learning is majorly when we have a huge data set, also mainly used in image processing.
Mm-hmm.
So you could think of deep learning as is a bit advanced than just machine learning.
Oh, okay. It's deep
So both, so both are subsets of artificial intelligence. But now deep learning is an application of machine learning where we use networks that try to mimic the human brain. That's why it's called artificial neural networks. Because we have the neurons in the human brain, the real one, but now what we use in deep learning is now artificial neural networks, just trying to mimic the working of the human brain.
What are called ANNs, right? You
Yes,
call them
neural networks.
Okay. And so now that you're talking about TensorFlow, how long have you been working with TensorFlow, and is TensorFlow something that you recommend to anyone else out there, and why would you recommend it?
I've been working with TensorFlow since my campus life, but majorly from 2017. I recommend it because there's a community that can support you in TensorFlow. There are so many. The documentation is wide. There's so much you can do with TensorFlow. And so from the community support side, from the many libraries you can use, I'd say it's the go-to library for deep learning.
So have you faced like any challenges while building models?
Well, I guess any person who does any form of development faces some challenges, but from a TensorFlow perspective, maybe just model hosting, but I'm aware of TensorFlow has provided a way to make that easy through TensorFlow serving, or you can also use Google Cloud for that. So I guess in most of the challenges you face, you could always get some assistance from the community or from tools that Google has already developed.
Okay, so and then with all this building model stuff, deep learning, do I need to have like a good understanding of mathematics to be able to like build you call them successful models, models that are working well? Do I need to like have a good grasp of mathematics?
I would say so, because these are computational models that are based on mathematics. So if you do not have any math background, you could probably build one, but then what happens happens when you need to tweak some things to understand what's happening in the background. So you don't want to do something that just looks like a black box. You want to understand what's happening in the background.
Okay. So there's no easy way in this. I cannot say I'm not good at maths and then I want to be planning.
You will need to get your linear algebra, statistics. It's important to understand some bit of calculus. For example, what we are talking about, gradient descent, that's differentiation, that's calculus. So the important concepts, I don't see how you would escape them totally.
Okay. And then there's always, I've always come across this term overfitting when it comes to machine learning. So how do you handle your overfitting issues, conditions when you're using TensorFlow?
Yeah, so as you've mentioned, overfitting, yes, that happens when...
Maybe you could also probably explain a little bit, maybe for someone who doesn't understand what overfitting is.
So it's basically when your model is not learning. We could say it's just memorizing. So it will do very well on the training set, but it will not do well on the test set. And you can always see that by plotting the loss function, and you notice that the loss function of the validation of your test set, validation set increases or is going up. So it means that the model is not learning. And so one of the ways, the first way is obviously to make sure your data is clean and all those things. But specifically in TensorFlow, there are things you would add like a dropout. So, the neurons, the layers are connected. So you can drop some of them so that the model is forced to learn. So you drop some layers when you're training using dropout.
Okay.
Another thing you can do is when you are setting your epochs, you can use callbacks to do early stopping. So for example, if you set 600 epochs, you could just use a callback, and then you just the early stopping callback, and then you set the number of epochs you want the model to stop training once it's no longer improving. So when using the callback, when the model stops improving, then it will just stop.
Okay, so when it comes to TensorFlow, and you've also, if I quickly remember, you talked about activation functions, and could you maybe explain us more about activation functions and optimizers, maybe in an easy way, if that's possible, so we can have optimizers, and which optimizers do you prefer?
Maybe if we go back to this slide. So what we were saying is that the network, when the data is passed through the network, you want to constrain the output. You can do this using what we call an activation function. So what we'll do is just constrain the output. So for example, let's say you are doing the example we're using of predicting churn. So in that case, you want your output to be the probability between 0 and 1. So if you're predicting churn, the probability above 1, it's always between 0 and your network to give you an output between 0 and 1. And so the kind of activation function you'd use for that is the sigmoid activation function, which you probably you'd pass at this stage. And so you pass in the sigmoid activation function, it will give you the result between 0 and 1, because you do not want to 2, because you cannot have a probability of 2, for example. But then if it's a regression problem, then you can use the ReLU, which will give you numbers above from 0 and above, for example. So in the hidden layer, for example, mostly we use the ReLU activation function, which will constrain our output to numbers 0 and above. And then for the output layer, you can use either the Sigmoid or the Softmax, depending on your case, or other activation functions depending on your case.
Okay, you have mentioned the ReLU. Maybe tell us more about it. Maybe the full. I remember the word.
It's the rectified linear unit.
Oh, yeah.
So it's the activation function which majorly we use it in the hidden layers. And the main reason it's used, it's that it's been proven that it generalizes well on your data, and then it's computationally simple and also gives you better performance. And so by default, this is the activation function that most people use for the hidden layers. So if you're just starting, that is where you'd obviously start.
Okay. What is the objective of backpropagation?
So the objective of backpropagation is to ensure that you're reducing the errors, you're reducing the loss function. And so what we are calling the loss function is that we use the loss function to compute the error. So for example, if you're predicting, say, price, you want to compute the error, like how often, whether you are getting it right or whether you're getting it wrong. And so you compute that using a loss function. For example, mean squared error. So what that means, that's why we are saying maths is a bit important, because, for example, in that case, you would look for the differences between the errors and then you would square them. So now what you want to do is that if, for example, your network starts with an error of 20, just an arbitrary example, you want to make sure that this error is reducing. So if this error is going up, then it means the network is not learning. So this error is supposed to be going down. And so the loss function you will use will depend on a case by case, also depending on the type of problem. If you're doing a classification, you use the classification loss functions, such as binary cross entropy. If you're doing a regression problem where you're predicting a number, then you use, for example, mean squared error or the root mean squared error. So backpropagation now ensures that those weights we talked about in the beginning are being adjusted to reduce this loss function.
Okay, so still in line of backpropagation, does it depend on gradient descent along error surface?
Sorry?
Still in line with backpropagation, does backpropagation depend on the gradient descent I had you mention earlier on along error surface?
So now what happens is that these errors will be computed using gradient descent. So now backpropagation is that process of going back. Now these are we call them feed forward networks. So it means the data starts from the input to the output. So it's passing through that. So that is moving forward. But now when you start computing the errors, now you start moving from the output backwards now as you propagate this, so that you can adjust the weights. So that's what we are calling backpropagation. That happens as a result of computing the gradient of the loss functions.
Okay. So on to another question: how can we validate a linear regression model using TensorFlow?
What do you mean by validate? Do you mean by validate?
Validate. So how will I put it? So, or maybe let me say how do you? I'm trying to understand the question. So, how do we use TensorFlow, or how can we use TensorFlow in linear regressions? I guess that is what the question is trying to mean.
So that's a regression problem. So it would be the same thing.
Mm-hmm.
So the difference would come when in the output. So you want your output to be a number. So you don't want to get, example, something between 0 and 1. So now the activation function you will use for the output layer will be, for example, linear or the ReLU.
Okay.
So that's a regression problem. But now if it was a classification problem, in the output layer, you would use another activation function, such as the Sigmoid or the Softmax.
Okay. Okay. So yeah, there is TensorFlow, there is PyTorch. What is the difference?
Well, they're just different libraries or frameworks for deep learning. So the difference is, we could say, is the API, the way both of them, like the syntax probably, and then who's sponsoring them. We know TensorFlow is being sponsored by Google and PyTorch by Facebook.
Yeah.
But then there are all deep learning frameworks that we can use.
Okay. So what's your favorite product built with TensorFlow?
Google Translator. Translate.google.com.
Can you tell us more about it? Or why favorite?
Well, sometimes you want to translate from one language to another. And when using it, I know that in the back, there's some bit of deep learning that is happening there. But then one that I know I use frequently is the keyboard, Gboard.
Mm-hmm.
For example, when you're typing on your keyboard, when the Gboard is able to learn from you such that it's able to predict the next word that you are likely to type. So when the moment you start typing, you see that you get a prediction for the next word. And so this makes it easier for you even when you're typing, like when you're texting. Also, a common one we're seeing nowadays is the suggestions we are getting on Gmail. Yeah.
Oh yeah. Yeah, that's what I noticed. It makes work so much easier, like I don't need to type like a whole sentence. It kind of knows, it sees one word I type and like automatically knows the next word that I really want to say. That's something really cool that I noticed. Yeah. So when we were talking about in the line of machine learning and all, and whether there's classification and there's also regression. So when should you use classification over regression?
So now that is obviously dependent on your problem. So if you're solving a classification problem, and a classification problem is where you are trying to predict some classes. So for example, we're taking the example of Gmail. Is this email a spam or not? Or taking the example of predicting whether a customer will churn, with a customer churn or not. So we're predicting some classes, whether something is true or false. So that makes it a classification problem. But then now when you're trying to predict a number, for example, the price of a commodity, the sales of a supermarket, items that will involve us predicting some numerical figure that is continuous, then that's a regression problem.
Okay, I think we'll close it here for the questions because we could continue this on, and might lose track of time. Yeah, but I really appreciate you for answering these questions and shedding some light on some areas that needed, for us to understand clearly, and also talking to us more about TensorFlow. So, Derrick, I really appreciate you. Thank you so much for taking your time to be with us to talk to us about deep learning. We've learned a lot. I cannot say I've learned one or two. I have learned more than one or two. Yeah. And I'm hoping that for those who are watching and for those who will watch later, they'll be able to learn more from this particular session. Derrick, do you have any resources that you recommend to anyone on deep learning or TensorFlow?
They can check my Medium. There's a lot of content there.
Oh yeah, your Medium. Okay.
Blog.
Oh, Medium blog. Still Derrick MWITI.
Yes.
Yeah. Okay. So if you need to find out more or learn what Derrick is doing, you can go check him on Medium. His name is Derrick MWITI. And also, if you still have maybe more questions you need to ask him, you can reach him via his Twitter handle. Yeah, I said at _ Derrick MWITI, if I'm not wrong.
At _ MWITI Derrick.
Oh, at _ MWITI Derrick. Yeah, sorry for that. Yeah, so thank you so much, guys, also for taking part in this. This would not have been possible without your input here. All of you tuning in, it's not easy at this time. Maybe you'll be using this time to do something else. That's why we really like to appreciate you for taking your time to join us here, and we hope that you'll continue taking part in our sessions. As we continue the TensorFlow series, we're not yet have not yet come to a close. We still have like one more session left. So watch out for any information about this particular session that is coming up next from the GDG Nairobi TensorFlow team. And yeah, and I hope we'll continue staying at home, quarantining safely, washing your hands, until we are all able to meet each other on a physical level. But for the time being, we're still going to have our sessions on air like this. And yeah, we're so happy to have you joining us all here. Thank you so much and feel appreciated. And at this particular point, I would like to wrap up this session. If Derrick, I hope you don't have anything else to say.
No, thanks for having me.
Okay. You're welcome. So yeah, thank you so much and see you next time. Don't forget to subscribe to the GDG Nairobi channel to get more information about our sessions.